Hello all. In this lecture, we will learn the Tabu search algorithm, which is a very common, one of the oldest and widely used meta-heuristic algorithm. We will learn the main idea of this algorithm, and I will explain the pseudocode of this algorithm, a formal pseudocode. We will talk about the critical choices of the Tabu search algorithm, which include the starting solution, when to stop, what should be the Tabu list length of the Tabu list, and how should we record the moves as Tabu moves. So we will learn basically what is the name Tabu. And we will learn about these Tabu criterion in more detail, and we will solve several example optimization problems with the Tabu search algorithm. So let's get started. Tabu search is one of the earliest meta-heuristic algorithms, which is based on local search. So it's an improving algorithm. It starts with an initial solution and it tries to improve the objective function value. In order to escape from local optima, it allows non-improving moves. Okay, so all of the meta-heuristic algorithms, if they are making some kind of a local search, they allow non-improving moves. Okay, so this is one of the differences of meta-heuristic algorithms from local search algorithms. One of the distinctive features of Tabu search is it uses memory. Okay, so this is very important for Tabu search. Memory. Whenever we talk about Tabu search, you need to remember memory. Okay, it uses memory to avoid cycling. We mentioned about cycling in the previous lecture, if you remember. So, for example, if we are trying to maximize, I'm giving an example on such a function all the time, but of course in integer programming we are making a search in a feasible region. Okay, we are trying to find the optimal solution in such a search space. But maybe it's easier to understand with such a nonlinear function if we try to find the optimum solution. Okay, so for example, if you start from here, by improving the search, you come to this point and then you allow non-improving move. So you make one step to this solution, and at that point there are improving new solutions. And if you go in that improving direction, you will come to this point again, and cycling through the set of same solutions all the time is called cycling. And in order to avoid cycling, Tabu search uses memory. We will talk about it later on. And also this memory, use of memory, satisfies diversification, the search to be diversified. So we will talk about these terms as well. What is diversification? But the basic meaning is this: if this shape is the feasible region of our search, or sometimes it's called search space, sometimes it's called feasible region. So if you make the search only in a restricted region of the search space, if you do not visit the other sides of the search space, then this search is not a very good one, and you most probably you will not be able to get very good results. In order to obtain good results, the search should be able to visit all parts of the search space. And in order to, this phenomenon is called diversification. Okay, and by the use of memory, Tabu search satisfies diversification. It can be said that this Tabu search is a general strategy for controlling a local search or some kind of an other inner search. So we can say that there is a local search algorithm here, and at the top of this there is the Tabu search procedure. So the Tabu search uses this local search algorithm again and again and again to find good solutions. So the Tabu search controls the inside heuristic, inner heuristic. And it is a meta-heuristic algorithm based on Glover, the first identified or developed this method. And this Tabu search algorithm used extensively in many different situations, in many different problems. If you search for Tabu search in Google, you will get hundreds and thousands of answers, academic papers as well. Now let's talk about the algorithm steps, and we will make examples, we will make clarifications furthermore. At this step, maybe some concepts is not familiar with you, therefore it may be difficult to understand, but later on as we proceed you will understand it better and you can return back to these steps and read it again and it will be more meaningful. So Tabu search starts, or all such algorithms starts with an initialization phase. This is usually numbered as step 0 of the algorithm. In this initialization step, as we said, Tabu search is an improvement algorithm. So we start a feasible starting solution. Okay, we need an initial solution. Here it says that we need, or we set an iteration limit Tmax. Okay. So we will talk about this Tmax. In fact, this is the stopping criteria. There are different stopping criteria that you can use. Okay. In this alternative version, the stopping criteria is given as a number of iterations. Okay, we will talk what is an iteration mean. What does an iteration mean? And we will talk different stopping criteria. Okay. And it says that set incumbent solution as the initial solution. So incumbent solution, if you remember from the branch and bound algorithm, incumbent solution is the best solution found until that point. Okay, best integer feasible solution that you have in your hand. So this is a memory, in fact. Okay, we are keeping the best solution in memory. But it is not the distinctive feature of Tabu search, not this memory. There is another memory we will talk about. Okay, this is one memory which keeps the best solution. Okay, then this T is the solution index, and the solution index is currently 0. And it says that no moves are taboo. So here we are keeping a list of taboo moves. We will talk about it. And initially, this taboo moves, there are no taboo moves. The taboo list, so-called taboo list, is empty. Step 1 of the algorithm identifies the stopping criteria, and basically it says that if you reach to a solution in which in the neighborhood, this M represents the neighborhood, in the neighborhood the non-taboo moves, if there are no non-taboo moves, that leads to a feasible neighbor. It means that you reach to a solution, you check its neighbors, some of the neighbors are taboo, forbidden, taboo means forbidden, you cannot jump to them, and when you look at the others, they are not feasible, so you say that, okay, stop. Or the second condition for stopping is, if you make necessary number of steps of the algorithm, so you reached this stopping condition that we set initially, and we will talk about this, how to set this, then we stop. Okay, so when you stop, the best integer solution in your hand, which is the incumbent solution, is the solution provided by Tabu search algorithm. Okay, so this is the stopping. If you are not stopping, then you need to make a move. So how do you make a move? So you choose a non-taboo feasible move from your neighborhood set, which means that you have some number of neighbors, some of them are taboo, forbidden, you cannot go them. You look at the others, you find the best okay, best neighbor, and you move to that best neighbor. When you move to that best neighbor, it means that you are updating your current solution. Remember the knapsack problem or the TSP problem that we made examples on. So when you check the neighbors, in fact, for example, we make pairwise exchange or insertion type heuristic neighborhood definitions. Okay, so when you find a neighbor with, for example, insertion, which is the best of all other neighbors, then you jump to this one. Basically, this step over here means that, okay, find the best of the non-taboo moves and jump to that neighbor. When you go to a new neighbor, you always need to check if that neighbor provides the best integer solution until now or not. It means that do you need to update your incumbent solution or not? If the new solution provides the best solution so far, then you need to update the incumbent solution. Step 5, okay, this is the distinctive feature of Tabu search algorithm. So you need to update the Tabu list. Again, we will make examples and it will be more clear, but Tabu list is a list of forbidden neighbors, forbidden moves. In order to avoid cycling, we use such a list, and this Tabu list, in fact, is the memory. Okay, so keeping such a Tabu list is the memory of the Tabu search algorithm. And how does this Tabu list works? So assume that you have such a list, and this list has a length. You can say that for 1, 2, 3, this list, let's say, has a length of 3. What happens when you make a move? You input that move at the top of the list. So you record that move. And if there is this last one is empty, okay, then you continue, you make another move, so you add the second move again at the top of the list. In that case, what happens? This first one moves to the second, and the new one goes to the first position. Then when you make a new list, a new move, you enter that at the top of the list, so everyone goes one step down, okay? Second position becomes third, first position becomes second, and the new move enters at the top of the list. And when you make another move, another record should be entered at the top of the list. But this time, what happens to the third one? Okay, there's no fourth position because the length of the list is 3. Of course, we will talk who decides on this. We will talk about it. But since the length is 3, there is no fourth position. So this move cannot go to the fourth position. Basically, it goes out of the list. Now it is not forbidden. It's not taboo anymore. Okay. So the taboo list works in this way. So when you make a move, you enter this move at the top of the list, and you remove the move at the bottom of the list from that list, so it is not forbidden anymore. Okay. We will talk about this, how to record these moves in the Tabu list, what should be the length of these, and etc. And then we increment our solution index. So when we are here, when we make a new move, it means that we make one iteration. Okay, so this T is the iteration counter. And when we do this, we return back to step 1. And when we return back to step 1, we check, okay, do I need to stop? Are these stopping conditions satisfied? If no, I will continue. If yes, I will stop, and the incumbent solution will be my solution. Okay, if not, currently I am at this solution, I will check the non-taboo feasible solutions, select one of them, make a move, if necessary update the incumbent solution, then update the taboo list and increment T by 1 and return back to step 1. So there is a loop over here we are following these steps again and again. Okay, so this is the general procedure of Taboo search. But as I said, there are individual characteristics of these steps that we need to talk about. What you should understand about these meta-heuristic algorithms, such as Taboo searches, there is no single Taboo search algorithm. Even for the same problem, for example TSP, Taboo search is a general guideline. Okay, so you can have different versions of Taboo search algorithm that solves the same problem. And what is different in these versions? You can select a different neighborhood. Okay, so for example, you generate or you develop a Taboo search algorithm which uses pairwise exchange. You can use another Taboo search algorithm which uses insertion. And depending on this selection of the neighborhood, some other characteristics may also change. And they are two different Taboo search algorithms. They are written for the same TSP. So when we say, okay, Taboo search algorithm, we solve the TSP problem using Taboo search algorithm, it doesn't give you all the details. It gives you the general idea. In order to be more specific, and if you are the one who is developing this algorithm for a problem, you need to talk about some critical choices. And what are these choices? What should be the neighborhood? Insertion or pairwise exchange, okay, or any other neighborhood definition. You should define the taboo memory. And we will talk about this. How are you going to list the moves or record the moves in your taboo list, and what will be the length of the taboo list? These are important criteria. Okay, so let me write it here. How to record and length of the taboo list. So the length of the taboo list means that for how long a move is forbidden. And the basic idea of this forbidding a move is, again, if I return back to this sketch again, so as I said, we may have cycling behavior because, for example, you start from here, you go to this one, and you find this local optima, and then you allow non-improving move, and then from here, when you go in the improving direction, you return back, and then you go and return back, so you make a cycling. So what do we do in Taboo search? When you make this improving move, non-improving move over here, you record the move that will return this back. Okay, this one, you forbid that move. You say that this move is now taboo. It means that when the search goes to this solution, it cannot return back, so it means that it needs to proceed. Then it goes in the improving direction, improving, and then it can come to this point. So forbidding such a move to avoid cycling and recording at Taboo search is the distinctive feature of Taboo search algorithm. Okay, when I say forbidding a move or recording it in the Taboo list, basically we don't want it to return back to the solution. We will of course talk about the advantage and disadvantage of having a shorter taboo list or longer taboo list, meaning that keeping a solution taboo for a long time or a short time. We will talk about this. Okay, so these are the criteria or selection of choices depending on the memory or the taboo list. Another criteria that you need to consider is how to select the candidate list. So it means that you are searching, let's say, your feasible region. Search space is this one. This is your starting solution. then you check the neighborhood of this solution, and you need to go to one of these. Usually in classical Tabu search algorithm, what is done is you evaluate the objective function of all the neighbors. So you generate all these neighbors, you evaluate their objective function values, and you go to the best one. If the best one is a taboo move, then you go to the second best one. If it is also taboo, you go to the third best one. And at each step, usually we go to a feasible neighbor. Okay, so from this one we go to a feasible non-taboo neighbor, and then when we are here we check its neighbors. Again we look for the best non-taboo move, and we jump to here. And the thing is, during these jumps the objective function value may be worse. So let's assume that we are maximizing. We may start with an objective function value of 50 over here. Then in the new neighbor it can be 70, so there's an improvement. Then when we are going from the second one to the third one, it may reduce to 30. Very worse, worse solution, and it's allowed here. But what do? We always keep the best solution in the memory. So this 70 is kept in the memory. And then we search the neighbor of this one, and then we jump to that new solution, and we are hoping that this new solution has a better objective function value. And if it has, we forget the old incumbent solution, update it, and go to this new one. Okay, so the question about selecting these candidates is this. Sometimes with some definitions of neighborhood, if you start from this solution, if you try to generate all neighbors, there may be hundreds and thousands of neighbors, and it will be very difficult to generate all of them and evaluate their objective function values. It will take time. For a heuristic, you have to remember this. We want it to be quick, and we want it to find the solution in a good solution in a short amount of time. So if you try to generate all neighbors, sometimes it can take a lot of time. For that reason, instead of generating all of them, somehow in some algorithms you may decide to generate a subset of these neighbors due to some let's say algorithm or limitation, and then among these you need to select one of them. And how do you select? Usually the selection criteria is to evaluate the objective function values for all of them and jump to the best one. Okay. So we need to define how we evaluate the function, how we compare these two solutions with each other, which is our objective function. We need to record the improvements in the solution values. As I said, we need to define our Tabu criteria, how long and how we record it. There is a so-called aspiration criteria in some meta heuristics, and what does it mean? In Tabu search, for example, we make some moves forbidden. Okay, so let's say that we start with an initial solution of 50 and we want to maximize the problem. Then we jump to a new solution which is 70. So now the incumbent solution is 70. The best solution that we find is 70. Then from this 70 we may go to 30, but the incumbent solution is still 70. Then from this 30 we are searching its neighbors, and we check for a neighbor, the objective function value of this neighbor. It has a value of 90. But the thing is, it is taboo. So it's forbidden. But still, although it's forbidden, it provides the best solution that we can find until now. So in that case, we override this taboo criteria, and even although it is taboo, we may want to go to this solution and we update our incumbent to be 90. And this is called aspiration criteria, in which cases you will allow taboo moves. Okay. So we need to define on long-term strategies when designing a taboo search, like diversification, as I told, and intensification. So these two, there should be a balance between intensification and diversification. These are two important concepts. Again, if we go back to our search space, so if you design a taboo search which only searches for a certain region of the search space, okay, so it means that you are making intensification. But making only intensification may not provide you the best solution. Therefore, your solution should also search for the other portions, other parts of your search space. And this is called diversification. Okay? If you diversify too much, meaning that if you jump from here to here, then to here, then to here, then to here, then to here, if you just diversify, again, you may not be able to find good solutions. Because maybe this region of the feasible space contains really good solutions, and maybe the optimal solution is somewhere around here. So if you just randomly diversify to the other portions, you may not be able to find that best solution. So what is the idea? The idea is, okay, diversify the search so that you can reach to different portions, but whenever you come up with a good solution, then intensify around that solution to find even better solutions. Then diversify to other region and intensify at that. Diversify to other region and intensify at that region. And in this way, we want to find the best solution. Okay, so any heuristic algorithm or meta-heuristic algorithm should satisfy a balance between diversification and intensification. Sometimes Tabu search algorithm is called as the best improvement strategy, local search with best improvement, because it always tries to select the best move, and this best move can be a move which worsens the current objective function, but among all alternative moves, you are selecting the best move. So what I mean is, you start with a solution, then you evaluate its neighbors, the moves. Okay, so let's say that you are maximizing, current objective function value is 50, and there is a solution here 20, there's another 30, there's another 70, there's 35, there is 15, and etc. You evaluate all of them, you find the best one for a maximization, this is the best one, then you jump to this one. Then for this 70, again you search the neighborhood, and you see that there is 5, there is 15, there is 30, there is 7, and etc. And you see that this is the best option among all others. Although it is worse than the current solution, we still go to this best solution. In this sense, it is called best improvement. So sometimes this algorithm is named as steepest ascent, mildest descent. So if you are maximizing, you want to increase your objective function as much as possible. So you are selecting the move which has the highest increase. But if it is not possible to increase, then you select the solution which reduces your objective function value the minimum amount, mildest descent. Okay, steepest ascent, mildest descent. But when you are selecting these neighbors, as I explained previously, some neighbors are taboo, so they cannot be selected. These are defined in the Tabu criterion. But as I said, if some of the taboo's moves are really good, although they are taboo, you may still jump to those solutions, and this is called aspiration criteria. And when we say taboo search, you need to remember the use of memory. It is very important for taboo search, and this memory is satisfied by taboo list. Now we can talk about this taboo moves a little bit in detail. So we call it a Tabu criterion. What is a Tabu criterion? The basic job of the Tabu criterion is to avoid visiting the same solution more than once. Avoid cycling. Okay, then how can we accomplish this? It's easy. So what you can do, you can store all the solutions visited during the search. Okay, let's assume that we are solving a TSP problem with, let's say, 5 cities. So assume we started with this sequence 1, 2, 3, 4, 5. And then we used, let's say, pairwise interchange. And the next one we moved to is 1, 3, 2, 4, 5. Then to this one we applied pairwise interchange and we moved to this 1, 4, 2, 3, 5. Then we applied pairwise interchange and moved to this one 1, 5, 2, 3, 4, and etc. We continue in this way. So what can we do? We can store all these solutions in the memory, all of them. Okay. And whenever we search for a new solution, let's say 1, 3, 2, 4, 5, in order to understand if this solution is already searched or not, we will compare it with each one of these. Is it identical with this one? No. Is it identical with this one? Yes. So it is taboo. Okay. So store all of them and check one by one. But the thing is, be careful. We said that the number of potential solutions in a TSP problem is n-1 factorial. And we are going to search, and we cannot search all of them. But with these meta-heuristics, we will still search a large quantity of these solutions in an intelligent way. And we will search thousands of solutions. And if, for example, if a TSP problem consists of, let's say, 20 or let's say 100 cities, in order to understand two sequences of 100 cities are equal to each other or not, you need to check every element if they are identical or not. Okay, so if you want to do this for 1000 times and at each time you compare 100 items, it will take a lot of time. Okay, so comparing these will take a lot of time. On the other hand, keeping all of these solutions in the memory of the computer will take a lot of time. Be careful when we are developing heuristic algorithms. The most important thing is time. We want a solution in a reasonable time, in a short amount of time. And if you design an algorithm which takes longer than the branch and bound method, then there is no logic. Okay, so you need to identify, or you need to find another way to overcome this problem. Okay, so we need to represent these solutions in an intelligent way so that it avoids returning back to the previous solution. How can it be? We will make examples, but let me show you one example. 1, 2, 3, 4, 5. Let's say this is the solution. Okay, and we made a pairwise exchange and we move to this one. So from here to here, what happened? What is the change? Ones are the same, fours are the same, fives are the same. The only thing is 2 and 3. Okay, so now this is our current solution and we are going to generate its neighbors by exchanging two cities. Okay, this one and this one, this one and this one, and etc. While trying to make those exchanges, if we forbid 2 and 3 to make a move, to make an exchange, then the new neighbor, we guarantee that the new neighbor is not the same with the previous one. Okay, basically, if we are in this solution and with a neighborhood operator, if we move to a new solution, what we want to do is we want to forbid the move that will take this solution back to the previous one. Okay, we want to forbid the move. So you don't need to keep the old solution. You just need to keep what move makes it to the returns it to the previous solution. So we just in our Tabu lists, we just list these solutions. We will make examples. To summarize what I have said, assume that we moved from sk to sk plus 1. So this is the solution in kth iteration, and this is the solution in the next one. So we jumped from this one to the other. And the change here is characterized by such a move. So we said, for example, 2 and 3 is exchanged. Okay, so that attribute is 2 and 3. So as a Tabu restriction, what do? We do not allow the moves that reverse the status for A. So if 2 and 3 are exchanged, then we forbid their exchanging again. So for this TSP, how can we do this? For example, this is given, let's assume that we start with this solution, and from this solution we move to this one. And what is the change in this new solution when you compare with the old one? 2 and 5 are exchanged. Okay, so now in order to move to the new one, I don't want to have this solution again, which is the old one. I want to forbid this move. Okay, so what are my trials for a new neighbor? I will try to exchange all pairs, this one and this one, this one and this one, this one and this one. I want to exchange all of them, and one of those exchanges is this one as well. And when I make this exchange, I will come up with my previous solution, which results in cycling. So I want to eliminate this one. So how can I do? I can say that, okay, I am forbidding the moves that involve 2 and 5. This is one alternative. Okay, I just keep in my tuple list 2 and 5 as a tuple. Okay, and any move that tries to exchange 2 and 5 with each other, I forbid it. But there are other alternatives as well. So what can I do? And as another alternative for this taboo, I can just forbid the moves involving 2 or 5. So what is the difference from the previous one, this new one? So basically, in this new one, in the previous one, I am just forbidding this move, exchanging these two. But in the new one, I am forbidding this move because it involves an exchange of 5. I am forbidding this move, I am forbidding this move, I am forbidding this move. Whenever a move includes 5 in it, I am forbidding. And also, I am forbidding this move, all the moves that includes 2. So 2 or 5. Okay, I am forbidding all these moves. Although some of them are unnecessary, because you see in this solution, if I exchange 3 and 5, the solution will be 1, 3, 5, 4, 2, and this is different than this one. But still, I can do such a forbidding, and this is more restrictive than the previous one. This kind of forbidding is more restrictive, and if you have such restrictive taboo in your search space, it creates diversification. It takes you from one side of the search space to the other side. Okay, so this helps diversification. What else? Instead of forbidding 2 of them, 2 or 5, I can just forbid the moves involving only 2. And if I do this, I will allow exchanges with 5 but not 2. So this will eliminate, or this will avoid me from returning back. Or I can forbid the moves involving just 5 similarly. Again, these two are more restrictive than this one, but less restrictive than this one. And all of them can be selected as a Tabu search or Tabu criterion in Tabu search. And before trying them, you cannot say which one is better. So you cannot say that, okay, this is very logical, so it is better, it will perform the best. No, you have to try different alternatives, and maybe some other alternative may provide a better solution. Let's make a quick example to understand how this taboo idea works in a knapsack problem. So this is a 0-1 knapsack problem. Let's remember the problem quickly. We want to select a subset of items to fill in our knapsack, and it has a capacity, and each one of these items has a benefit, a utility for us, and each one of them has their own weight or volume, and we have to select those items to maximize our total utility without exceeding the capacity of our knapsack. Let's assume that we are developing a Tabu search algorithm for this problem, and inside this Tabu search algorithm, we will be using the flip neighborhood. Okay, basically, we already made a local search algorithm for knapsack. We will perform that local search algorithm with the idea of this taboo, forbidding some of the moves. Okay, we will use the flip neighborhood. What was this flip neighborhood? If you remember, we represent the solution of a knapsack with a sequence of zeros and ones. Basically, for example, if you have 4 items, 1, 0, 0, 1, for example, means that we are taking the first item, not taking the second and third items, and we are taking the fourth item as well. So in order to represent each one of these items, we have a 0 or 1 indicator. Okay, and in flip neighborhood, basically, what do we do? Given this initial solution, we generate its neighbors by just flipping or swapping the value of the variables one at a time. So if you flip the value of the first variable from 1, it returns to 0, and we have 0, 0, 1. If you flip the second one, the first one we keep it the same, and the second one we flip its value. Okay, so we are flipping one at a time. So it means that for this initial solution, in total we have 4 alternative solutions. Okay, so this is 0 as well. Sorry, this is 1. So we are going to use this flip neighborhood, but whenever we flip, for example, we move from one solution to another one, for example, this one, what happened? We flipped the first variable. So we will keep this 1 as taboo, and it will be called the taboo criterion. So it will stay in the taboo list for a duration of time. Temporarily, we will forbid that flipping the first move again. Okay, and by this way, we want to avoid cycling. So if it is inside, or if we take it, throw it out of our bag, we will not allow them to come into our bag again, or if we took them inside the bag, we will not allow them to go out of the bag for a certain amount of time. Okay, so this is the basic idea. Let's consider this knapsack problem to include 4 items, and let's assume that this is our starting solution. Okay, this is the starting solution. So let's first thing, of course, we start with the taboo search to be empty. Initially, the taboo list is empty, and we generate all the neighbors of this solution, as in local search algorithm. So all the neighbors of this solution are like this. For example, if we flip the first variable, we reach to this. If we flip the second one, then we come up with this solution. Flipping the third one brings us this solution, and flipping the fourth one leads us to this solution. Okay, we will represent feasible neighbors with orange color and infeasible neighbors with brown color. Okay, so for this one, when we consider all alternatives, and currently this is our Tabu list, currently Tabu list is empty. There are no forbidden moves. What do? Our current objective function value is 11, and from this 11 we will jump to the best one. And if you compare the neighbors, the best feasible neighbor is this one. So our next solution will be this. And while going from this solution to this one, what happened? We flipped the third variable, right? So this one from 0, it is flipped to 1. Okay, now what do? We set this one as our current solution, and since from the previous one to this solution we flipped the third variable, we include it in our Tabu list. So we keep 3 in our Tabu list, okay, and we will use that Tabu list while generating new solutions. We will prevent or forbid flipping the third variable. And current objective function value is 20. Previous was 11. So our incumbent, if we keep track, our incumbent is 20. The best solution that we identified until now is 20. Okay, now we generate the neighbors of this solution, and we generate all the neighbors. So if we flip the first variable, we will come up with this solution, but it is infeasible. If we flip the second decision variable, we will end up with this solution. If we flip the third one, we will return back to this one, but it is a Tabu move, but still we generate it, okay? But it's Tabu. And how do we know that it's Tabu? Because we flip the third one and this 3 appears in our Tabu list. Okay, and then if we flip the fourth one, we go to this solution and it's also infeasible. So when we look at the feasible neighbors, we have this alternative and this one. This one has a better objective function value, but since it is Tabu, we are not selecting that one, we are going to this one. Okay, so the next solution becomes this one. Okay, this is our current solution. And since from here to here we switched or we flipped the second variable, we enter this into our Tabu list from the top, from the beginning of the list. So the 3 moves 1 step right and 2 enters to the list from the left. And so, for example, our Tabu list length can be 1, 2, 3, 4, 5 characters. So these 3 at each step, these 3 will move 1 step back, 1 step back, 1 step back, and when it is here, when it moves 1 step more back, it will be out of the list. So it will not be forbidden anymore, meaning that we are forbidding these moves for a temporary time. And what is the incumbent solution until now? Incumbent, the best integer solution that we realized until now is 20. We encountered this solution here. The current solution is 9. Okay. And if when we moved from here to here, the objective function value worsened. But the incumbent is still 20. It never worsens. Incumbent solution either improves to a better one, or it stays the same. It never worsens. Okay, so now this is our current solution. We will generate its neighbors, and again there are 4 neighbors depending on what we are flipping. So if we flip the third one, we will reach to this solution, but 3 appears in our list. So it means that this neighbor is taboo. If we flip the second decision variable, we come up with this solution, but 2 is in the list. It means that when we flip 2 and find the neighbor, it is also taboo. When we flip the first one, we come up with this solution, and when we flip the fourth one, we come up with this solution. So there are 4 neighbors, but 2 of them are taboo, and among these two, the best alternative is this one, so it becomes our next solution. So since we are flipping the fourth variable here, we need to enter 4 at the top of the list in the next step. So 2 will go 1 step right and 3 will go 1 step right. And then we will continue in this way. But now you can identify something important about these taboo moves, the lengths of the taboo moves. Assume that in this question, the length of the taboo list is 4. Okay, so what happens in the fourth step? This 3 will move to the last position. Then we will have 2 over here. We already have 4 here, and we will have 1 here. And we already have just 4 decision variables, and all of them are taboo now. So there are no feasible neighbors at all. So if the length of this taboo list is too much, too long, it means that after some point there will not be any feasible neighbors. And in that case, in fact, you are not making a search. Therefore, the length of the taboo list should not be too long. But if it is too short, again what you can encounter is cycling, because in this example back again, so if you moved from here, if you make a move forbidden for just 2 steps, you can go to, let's say you went to here, and then in the second step you went to here, and then the first move is not taboo anymore, and then you can return back to here, and then the second move is not taboo anymore, and then you can return back to here. So you will have a cycling with 2 steps. So there should be a balance. It is very important. There should be a balance for the length of the taboo list. If it is too short, you may end up with cycling. If it is too long, you may prevent all the feasible neighbors so that you cannot make a good search. Let's consider a knapsack example and solve a knapsack example with Tabu search algorithm to understand its mechanism better. So this is the example that we are going to solve. We are trying to maximize these. There are 4 items, and each item has its own weight, and the total capacity or total limitation on the weight is 3. So in order to have a Tabu search algorithm, we need to know the parameters of the Tabu search algorithm. The first parameter is we are said that we need to use the flip neighborhood. So we may use different types of neighborhoods, but in this example we will use flip neighborhood that we already learned. Then we need to know the length of the taboo list, and it's given as 2 iterations. We need to know the initial solution, and it is given as 1, 0, 0, 0, which means that take the first item, do not take the others. Of course, we need to know if it is feasible or not, and in order to understand if it is feasible or not, you just plug in the values in the constraint over here, and you see that 2 is less than or equal to 3, so this solution is feasible. And we need to know its objective function value, and in order to understand it, just put the values into this objective function, and you will see that this initial solution has an objective function value of 18. Okay, so we also need to know the stopping condition criteria, and the stopping criteria is given as Tmax equal to 5 steps, which means that make 5 iterations and stop after the 5th iteration. I'm going to write the solutions in such a table. Of course, it is not necessary, but it will be easier to solve the problem with such a table. And at each step, you will understand what we are doing. So we will start from step 0, okay, the initialization step. So when t is equal to 0, this initial solution is given to us. So that initial solution is 1, 0, 0, and 0. And the objective function value of this solution is 18 when you put it in the objective function. And incumbent value, what is the best solution that we identified until now? We always keep it in memory, so it's 18. Now I need to look at the neighbors of this solution. 1, 0, 0, 0. So what are the neighbors? The first neighbor is flipping the first decision variable x1. It will give me 0, 0, 0, and 0. If I flip the second one, it will be 1, 1, 0, 0. If I flip the third one, it will be 1, 0, 1, 0. And the last one gives me 1, 0, 0, 1. Now I need to select one of them. The taboo list is currently empty, so I need to keep track of the taboo list as well. And since none of them are taboo, I can select the best one of them. So I need to calculate their objective function values. For this one, if you put to the first of all, it is feasible because it satisfies the constraint 0, 0, 0, 0, so less than or equal to 3. And when you put it in the objective function, you will get 0. For the second one, when you put it into your constraint input instead of x1, x2, x3, x4, you see that this 4 is not less than or equal to 3. So this solution is infeasible. Okay, basically you cannot consider it as a feasible neighbor. The third one is feasible with an objective function value of 29. And the fourth one is feasible with an objective function value of 32. Okay. So which one is the best one? The best one is this one. So I will keep the variable which is flipped or which is complemented. Flip or complemented, the same meaning here. Okay, in my taboo list. So which variable is complemented? For when the fourth variable is complemented, right? When xj is equal to 4, in order to obtain this solution from this one, x4 is complemented. And what is the change in the objective function? So current objective function value is 18, and the new objective function value is 32. So the change in the objective function is 32 minus, let me write in this way, 32 minus 18, which is 14. So the objective function is improved by 14. Okay, now this is the first step. We decided the new neighbor. And now here I'm going to also write my taboo list. Okay, so I will write in this way, taboo list. And remember the length of the taboo list was 2. So this is 1 and this is 2. And when we move to the first neighbor, we are inserting 4 at the top of the list. Second position is empty. Okay, now we can go to the next step, which is 1. And in this next step, since we flipped the fourth variable, we move to this solution. And the objective function value of this solution is 32. And since this is the best solution we identified until now, we update the incumbent value. It is 32. Now we are with this solution 1, 0, 0, 1. I need to consider it is neighbors to select the next one. So flipping the first one leads to 0, 0, 0, 1. This is a feasible solution with objective function value 14. Flipping the second variable or complementing the second variable leads to this one, which is infeasible. Complementing the third one leads to this solution, which is also infeasible. Just check with your constraint. And flipping the last one leads to this solution, which is feasible and which has an objective function value of 18. Now I need to select one of these, but remember this one is taboo. Okay. So it means that there is only one feasible neighbor, which is this one, and I should select that one, which means that I am complementing the first variable, and the objective function value is 14, which means that from my current solution, which is 32, I am going back to 14, so the change in the objective function value is 14 minus 32, which is minus 18. This minus tells me that it is a non-improving move, but I am keeping my incumbent solution, my best solution. Okay, now I can input the new step. Let me just delete this part, and in t equals 2, now my current solution is this one with objective function value equal to 14, but the incumbent is still 32. You see, incumbent value either increases, improves, or stays the same. And now I need to identify the neighbors of this solution. Let me write it here. So the first neighbor is this one, the second neighbor is this one, third neighbor is this, and the fourth neighbor is this one. By the way, don't forget to update the taboo list. So whenever we flipped or complemented the first variable, the previous taboo moves to the next position, and the first taboo enters the list from the top. Okay, now this first solution is feasible with an objective function value 32. The second one is feasible with an objective function value of 39. The third one is feasible with an objective function value 25, and the last one feasible with objective function value 0. Among these, the best one is this, which is a result of flipping the second decision variable, and when you check the taboo list, it is not in your taboo list. So we can go to this solution, which means that we are complementing the second variable, and the change in my objective function value is from 39 minus 14, it is plus 25, an improvement of 25 units. Okay, now the next step. So how many steps did we go until now? From 0 to 1, we make one step. From 1 to 2, we make second step. And from 2, from this solution to the new one, we made another step. And our new solution is this one. So let's update our taboo list. So what happens to this 4? Now it is out of the list. What happens to this one? It moves one step down. And what is the new taboo move? It is 2, which enters at the top of the list. Okay, now the objective function value of this new solution is 39. Since it is better than our previous incumbent solution, we update the incumbent solution as 39. Okay, now we need to find the neighbors of this solution to identify the next solution. So the first one is 1, 1, 0, 1. Second neighbor is 0, 0, 0, 1. Third one is 0, 1, 1, 1. And the fourth one is 0, 1, 0, 0. Okay, so this solution is infeasible if you check it. This solution has an objective function value of 14. This solution is infeasible. And this solution has an objective function value of 25. So among these, This one has the best objective function value, which is obtained by complementing variable x4. And when you look at the Tabu list, x4 is not in the list now, so I can make this move. So we temporarily forbid that move, and now we can do that move again. So it means that j equals to 4. You see, the same variable can be complemented twice after waiting at least 2 periods of time. And okay, now my new solution value is 25, and my previous solution was 39, and there is a worsening in objective function value by 14 units. Okay, the next solution, which is the fourth step, we move to this solution 0, 0, 0, 1, 0, and 0. The objective function value is 25, and incumbent is still the previous one, 39. And now I need to find the neighbors of this solution. So the first one is 1, 1, 0, 0. The second one is 0, 0, 0, 0. Third one is 0, 1, 1, 0. And the fourth one is 0, 1, 0, 1. And of course, we need to update the Tabu list. So what happens to this second position? It is out of the list. The first position moves to second, and the new shift, the new move enters at the top of the list. Okay, the first one is infeasible if you check the constraint. The second one is feasible with an objective function value of 0. The third one is infeasible. The third one is feasible with an objective function value of 36. And the fourth one is feasible with an objective function value of 39. Okay, so among these, this has the highest value, but when you look at the Tabu list, you see that this fourth variable is in the Tabu list. And now you can check for aspiration criteria in such a situation. If this objective function value is better than your incumbent solution, then although this is Tabu, you can continue with this one. So that's aspiration. And when we check it, our incumbent solution is 39, and this solution is also 39. So it is not better than my incumbent solution. Since it is Tabu, I'm not selecting this one. Okay, so the next best alternative is this one, which is obtained by flipping x3. So it means that I am going to move to this solution. Let me erase this part. So my j will be here equal to 3. And let's update the Tabu list. So this is out of the list now. This moves to the next position, and 3 enters at the top of the list. And what happens to our objective function? So from 39, our previous solution was 25. So the improvement value is 11. So in this delta objective, we are finding this delta obj by the objective function value in iteration k plus 1 minus iteration k. So we are not subtracting the incumbent solution. We are subtracting the previous current solution, okay? Not incumbent solution, but this one. It just shows you what's the improvement and etc. It's nothing important. Even if you don't write it here, it will not change. But in simulated annealing, we will be using that delta obj values. Okay, now we move to the fifth solution. Basically, in the fifth one, we have this 0, 1, 1, 0 with objective function value 39, the incumbent 36, and incumbent is 39. Okay, now do we need to make a new iteration? No, in fact, because we already made 5 steps. From 0 to 1, this is one step. Second, third, fourth, and fifth. If you make one more step, it will be the 6th step. So from this initial solution here, we find our first solution, second, third, fourth, and fifth. So when you find your 5th solution, you stop. Tmax 5 steps means finding the 5th solution after your initial solution. So the Tabu search algorithm stops here, of course, with these parameter settings. Now, if you change this length of the Tabu list from 2 to 1 or to 3, you may come up with a different solution. If you start from a different solution instead of this one, you may end up with a different solution. If instead of using 5 steps as the stopping criteria, if you use 50 steps or if you use 2 steps, you may come up with a different solution. If instead of flip neighborhood, you use a different neighborhood, then you may end up with a different solution. This is a good example to show the mechanism of the basic Tabu search. But all these parameters must be determined by you. If you want to develop your own algorithm, you have to decide on these parameter values. And these parameter values affect the performance of the Tabu search algorithm too much. And this is a Tabu search algorithm for the knapsack problem. If you want to solve the TSP problem or set covering problem or any other problem with Tabu search algorithm, you need to identify the neighborhood, you need to identify the Tabu list, how will you record these Tabu moves, what will be the length of the Tabu list, how will you find your initial solution. Okay, you need to identify all of them, and while identifying those, you need to have a balance between intensification and diversification so that at the end you will end up with a good solution. Okay, so this is the end of our discussion on Tabu search algorithm.